For the first example of finding surface area, let's take a look at this problem. So if f of x equals sine of x from x equals 0 to x equals pi, and we want to revolve that about the x-axis and find the surface area of the solid of revolution that is generated from revolving that region about the x-axis. So let's think about what that would look like. Just real quick, let's do a graph. It's an easy one to graph here. So from 0 to pi, let's let that be 1, that be -1. So the sine curve would look something like that, and we want to revolve that about the x-axis. And so we'd end up with something that looks like that. And then we could just show the three-dimensional bands here going around. So we're looking at a surface of revolution, or solid of revolution, that we want to find the surface area of that looks something like that. I got a little better on my graphs. I'll get better there as we go here. Okay, so if we want to find that surface area, then let's take a look real quick. I just pulled those formulas from our actual derivation of the surface area over here. So if we want to find a surface area, the formula that we have is about the x-axis. The formula that we have is the integral from a to b of 2 pi y ds, where ds is actually down here. We can see the two possibilities of how we could represent ds. ds is equal to the square root of 1 plus dy dx squared dx, or the square root of 1 plus dx dy squared dy. And again, if what we're doing there is we're thinking of taking just these tiny little line segments on the surface and rotating it around the axis of revolution to create these bands that we're finding the surface area of. So let's go back over here to our example and just write that down. So surface area is going to be the integral from 0 to pi, in this case, of 2 pi y ds. So that's the formula that we're going to use. ds being the square root of 1 plus dy dx squared dx. And we'll give ourselves a little bit more space here. Okay, so if y equals the sine of x, let's go ahead and take the derivative, do a little bit of simplification, and then we'll set up the integral. So what would dy dx be? Similar to how I set up the arc length problems. So if we take the derivative, dy dx is going to be cosine, and 1 plus, let's go ahead and do the whole thing, 1 plus dy dx quantity squared is going to be 1 plus cosine squared of x. Okay. Now I think we're about ready to set up this integral. There we go. So the surface area would be equal to the integral from 0 to pi of 2 pi times y, so our y is sine of x, times the square root of 1 plus the cosine squared of x dx. And now we get into all of our integration strategies. So how would we integrate this particular problem? And I look right here at this square root, and I see that I have 1 plus the cosine squared of x right there. And I'm thinking that that looks an awful lot like a 1 plus u squared, but I would have to have a du. And then I notice outside of the integral, since we had that multiplication of y in the surface area formula, we actually have a sine of x. So my first step here is going to be to let u equal the cosine of x, which makes du equal negative sine of x dx. And then sine of x dx would be negative du. And I'm going to make those substitutions, so doing a u sub first. You could combine the u sub and the trig sub here because we are going to end up with a 1 plus u squared. And then our second integration technique we'll apply here will be the trig sub. If you would prefer, you could do those two steps together. I did an example with one of my classes yesterday where the preference was to do it as two pieces, so I'm doing that on this one. All right. So then we've got the integral from x equals 0 to x equals pi of 2 pi. Now we're going to make that substitution with the sine of x and dx, but it's going to become a negative du. So I'm going to put the negative right here. Negative square root of 1 plus u squared du. And I just noticed that I'm not going to have enough room because my second example is showing up. So let me pull that out of the way here. Okay, back to our integral. So one quick little note on this one, when I have that minus right here, I can go ahead if I want to, and I can flip these bounds. Actually, I'm not going to flip the bounds quite yet. We will flip the bounds, but what I want to do first is switch them. I just noticed as I was highlighting them that we still had them in x. So let's go ahead and switch those bounds now in terms of u. So if x equals 0, then the cosine of 0 is 1, and if x equals pi, then the cosine of pi is negative 1. So our u bounds are from 1 to negative 1, but with that negative right here at the front of the integral here, we could actually flip these bounds, and that would actually make sense anyway to do that. So I'm going to go ahead, flip the bounds, just clean up this integral before we do our second integration technique. Flip the bounds. Simply just to clean it up. So this will now be just 2 pi times the square root of 1 plus u squared du, and it will run from lower bound negative 1, upper bound 1. Okay, so now our second integration strategy that we're going to need to apply here is going to be a trig sub. So let's take this guy and let's apply a trig sub. So to do the trig sub, since it's 1 plus u squared, let's let u be equal to, actually we'll do that, right? U equal the tangent of theta. And of course we'll have to make sure that theta is between negative pi over 2 and pi over 2. So I'll set up my bounds here. And my du is going to be secant squared of theta d theta. And we're going to make those substitutions. I could draw the triangle, but I think I'm going to change the bounds instead. So let's skip writing in the triangle right now and remember that this was u equals negative 1, u equals 1, and this is 2 pi square root of 1 plus the tangent squared of theta times the secant squared of theta d theta. And now the bounds, if I do that, so rather than drawing the triangle and going back in terms of u, if I change the bounds, I won't have to do that. So when u equals negative 1, the tangent would be the tangent of the value of theta that would generate a tangent of negative 1 is negative pi over 4. And for positive 1, theta, the angle would have to be to give tangent of pi over 4 would give us a positive 1. Okay, so doing a little switch on the bounds right there too. So switching my bounds. So I don't have to go back in terms of u. Well, now we also have a 1 plus tangent squared here, which we know is secant squared of theta, but we're taking the square root of that, so that's actually the absolute value of the secant of theta. But when we made the substitution here, the trig substitution, we restricted the bounds on theta, so secant is going to always be positive here. So since secant is always positive, we are going to go ahead and drop those absolute values. Now we can write our integral all the way here as just theta from negative pi over 4 to theta equals pi over 4 of 2 pi times secant of theta times secant squared of theta d theta. And those two become just the integral of 2 pi times secant cubed of theta d theta from negative pi over 4 to pi over 4. And again, that's one of those integrals that we proved in class a while back when we were doing trig integrals, and we can reference our useful integrals, or maybe you have this one memorized. This is one I have committed to memory. So this is 1/2, scroll up a little bit. So this is going to be 1/2 secant theta tangent theta plus the natural log of the absolute value of the secant of theta plus the tangent of theta. And we'll evaluate that from negative pi over 4 to pi over 4. So since I changed my bounds as I made each of my substitutions, I don't have to go back and back substitute at this point. I can go ahead and just plug in my bounds. So this ends up being equal to 1/2, and then the secant of pi over 4 is going to be root 2, and the tangent is going to be 1, plus the natural log of root 2 plus 1, when we plug in pi over 4, minus 1/2 times, now the secant of negative pi over 4 is root 2, but the tangent is negative 1. So we get negative 1, and ln of the absolute value of root 2 minus 1 when I plug in the negative pi over 4. And now we actually have found the value of the integral, but this is a pretty messy answer that could be cleaned up quite a bit. So let's do that. So this ends up being, if I were to pull the 1/2 out, this ends up just being root 2 plus the natural log of the absolute value of root 2 plus 1. And then we end up with a minus of a minus. So this is plus root 2 minus ln of root 2 minus 1. And continuing to simplify, just 1/2 times 2 root 2 plus, and use my rules of logarithms, natural log of root 2 plus 1 over root 2 minus 1. And that is a little nicer, a little cleaner, shall we say, of an answer. And there we go. There's our first example of surface area.